Hello, welcome to this course on quantum computing. This course is designed for students who are coming right out of high school and maybe in the first year of university in some STEM area, with a particular focus on beginning computer science students. The idea is to introduce quantum computing so that even people with no background in quantum physics can start programming a quantum computer. This course will start with a rapid transition from classical mechanics to the basic concepts in quantum mechanics, and then we will quickly build on it to start writing small programs using basic quantum algorithms. However, before we start writing our quantum programs, I would like to introduce some required mathematics, especially basic linear algebra and the language of quantum computing algorithms, which is based on Dirac's bracket notation. In this first lecture, we will start with a transitionally introduction to quantum mechanics by starting with a recap of basic concepts of quantum mechanics. So, let's dive into the lecture today. So we will start with the short introduction of where classical physics applies and where we need quantum physics, and I will introduce the quantum mechanics postulates. But to do that, I will sort of recap what you might have learned in some introductory classical mechanics course, or maybe in general in some science class. I will start with the postulates of classical mechanics just to sort of give an equivalent idea of what classical and quantum mechanics have in common and where they are different. So let's dive right into it. So let me start with a recap of what classical world look like. So where we use classical mechanics. So a typical example that we can think of is, let's say, an apple falling, from a tree, and we want to determine how long it's going to take before it hits the ground, and if you are giving some height age, so like what is the time required, or maybe what's going to be its trajectory, which in this case is going to be like a simple trajectory. Or we can think of another problem of, let's say, somebody is hitting a football, and we want to see where the football go after the hit. So what's going to be its trajectory, how long it's going to take, and how far away it's going to strike the ground. And maybe if you want to go deeper, what would be its velocity at the time of hitting the ground, what height it can go on, and so on. And there are sort of other types of problems in classical world that we can think of. For example, how a fluid flows through a pipe, or maybe how to construct a bridge or a building, so that it has some required features where we might have several mechanical parts, uh, stacked on each other and so on, and we want to maybe work out the stability or its resilience to earthquakes and so on. And similarly, there can be other problems like how do, for example, gases behave when you compress them, in some cylinder. So here is some gas. Maybe we want to work out the efficiency of some engine. Uh, to construct some machinery. So, this is the classical world that we are talking about, and as you see that all of these things, they have this thing in common, that they represent sort of a macroscopic world that we live in. So that's what the physics started to explaining when the physics started, several hundred years ago, and Galileo and Newton and other scientists, they started, coming up with the laws. So, in a nutshell, the classical world is sort of the macroscopic objects that we see. And even when we think of these macroscopic objects, like as a composite object, for example, a building or a bridge or maybe gas or liquid. So, we think of the big thing as composed of, smaller parts. And then the idea is that even if we want to work out how the whole part is doing, all we have to do is, try to understand how the individual particles are doing, and then we add up their behavior. However, like about 100 years ago or so, maybe 120 or 30 years right now, people started realizing that the microscopic world is sort of there are some properties of that microscopic world. For example, when they started looking at atoms and electron, and there was a Bohr's model of a central nucleus, and then orbiting electrons, and then maybe the gases at very low pressure, and when they were interacting with some light from the outside, or maybe if you connect them in if you connect two electrodes and pass electricity. And we saw that the behavior of these systems, it doesn't sort of get explained by what our understanding was of the classical world. So slowly a new understanding, or a modern understanding of the world started to come around. So even though, like, even the macroscopic world in principle obeys the laws of quantum physics, but since the quantum physics agrees with classical physics when we are observing the macroscopic world, so generally we restrict the quantum mechanical description, since it's more complicated, to only the phenomena where we can't explain it using the classical world. For example, the interaction of light with the atoms, and there are a bunch of other examples. For example, we can talk about uh, uh, if, let's say, white dwarf star, which even though is a macroscopic object, or maybe even neutron star, even though these are macroscopic objects, but their properties, they are essentially determined by the quantum physics. And similarly, there are other macroscopic objects that we can think of. For example, if I have a superconducting material, which is generally a material which has been cooled down to a very small temperature, usually very low temperature, and then its properties, even though it's a macroscopic object, it's only understood in terms of the laws of quantum physics. So quantum physics is, we mostly use it to explain the macroscopic world, but sometime even the macroscopic world's description and understanding requires quantum physics. And in all of this description, what we observed all the way, starting from Planck's theory of how the electrons get ejected from a metal. Let's say if we have a metal and some light is striking on its surface, people discovered that it ejects electron. So starting from this photoelectric effect, people started observing that one of the fundamental property of these systems is this, that their energies are quantized. For example, uh, it's not that they can have any energy as they like, but energy could be, suppose, some E naught, or could be some E1, or could be some E2, E3, and so on. So this quantization of energy is actually what gave rise to the word quantum in quantum physics. So many of these, systems, they have this property in common. So either energy or some other property, or maybe more than one properties of the system, they are quantized. Like only discrete, values are available. For example, we quickly discovered that the atoms, they uh, they have a system in which, if there is a central nucleus, the electrons can't just go anywhere. So there are only allowed orbitals where the electrons can go. So, like, even the distribution for electrons to be around a nucleus, it's quantized in a sense that only certain spatial distributions of electrons are allowed. For example, they can either be in spherically, symmetric shells, or maybe there are dumbbell shells, shaped shells that they can be in. So the major sort of attribute of quantum world is that some property is quantized, that there are only few I mean, it can be infinitely many, but there are like discrete allowable states of a quantum system. But it doesn't mean that in quantum world only discrete states are allowed. It can actually go to a continuum as well, where there's a continuous spectrum of states that is available. But in this course, we will mostly be concerned with systems that has quantized set of states. So, to describe this quantum world, a new set of laws, and it's a whole domain of application was discovered. So this is called the quantum physics or quantum mechanics. We usually use them interchangeably. So I'm going to introduce the basic principles of quantum physics. But before I do that, let me sort of recap what we know about the classical physics. So let me start with the postulates of classical mechanics. So the fundamental sort of belief that governs all of the development of classical mechanics and its application is this, that the state of a classical system is given by its position vector and its momentum vector. And in 3D, this position vector can be, let's say, a column vector with three component, and this momentum vector can also have three components. Okay, so, and these components are real, and they are directly observable, which means that we can set up measurements to measure the all three components of position and all three components of momentum of any particle that might be moving around in space. So suppose there is a particle with some mass m1, and it has some position x1 and some momentum p1. So its components can be measured directly. And Because of this, the classical mechanics is sort of easy in the sense that everything seems realistic, that we have a particle which has a position and momentum, and we can measure position and momentum. For example, you might have uh, a system set up which emits light, and the light goes on to the particle and comes back. So using this time of flight, you can find its position, and by computing the change in position, and with a clock that we have over here, we can compute its speed, and from speed we can find momentum. So this is sort of the first governing belief, that we have we can describe the state of a system by its position and momentum. And you see these position and momentum vectors, they are not only real and directly observable, but are also continuous. So uh, so and there's sort of not a lot of restrictions what values x and p can take, except that they shouldn't be infinite. Like all finite values are possible for these x and p. So in principle, all so basically, so all space and all possible values of momentum are available to be assigned as a state of the particle. And we can actually define a joint space sort of the particle, where which is like six dimensional. So there are three dimensions for position and three dimension for momentum. So a point in this in this space, which we can call phase space, describe the state of the system, and any finite value for the coordinates of this phase space, they are allowed states of the system. And let me insert another slide. And because of the this belief that we have, that measurements can give us p and x of of any particle without changing x and p. So this is actually like a second postulate, you can say. So this was the first postulate, that the state is given by x and p, and we can think of this as a second postulate, that measurement can give us the exact values of p and x of any particle without changing it, without disturbing the actual values. So this is a second belief that we have in the classical world, that governs all the physics that we see that we apply to the classical physics. And it probably makes sense, because the classical systems are mostly macroscopic systems, and usually we can find their position and momentum using light, which doesn't when light impinges on any massive particle, and if this is not a very strong light, we can imagine that its position and velocity doesn't get disturbed much by this light. So because of this, actually, there are many nice features that we have. For example, we can copy the state very easily and prepare another state. For example, you see that somebody is running with some speed v. You can measure this person's speed, and then have somebody else move along with exactly the same speed, and its position. So sort of we can prepare a copy like this. Or we can think of something else. For example, in a hard drive, you have a space where you have magnetized the state in a certain direction. You can measure the state, and then prepare another state over here, in which the majority of the particles are magnetized in this way. So if this is state 1, you can copy this one over here. So copying of state is allowed without destroying the previous state. Okay, so let's go to the next very important postulate, and that is the evolution of state. Evolution of the classical state, or you can also say the change in state. And for this purpose, we can actually use Newton's law, that the rate of change of momentum of any particle is given is equal to the force that is applied on it. So if there is no force, the momentum doesn't change, which means that if it is still, it's gonna remain still, and if it is moving with constant momentum, it will keep moving with constant momentum, and its trajectory will change from constant momentum state only if there is an externally applied force on this. So this law can tell us how to find the next state. For example, uh, momentum at some time t can be found by integrating uh, this force. So the change in state is found by Newton's second law, and that's the third sort of governing postulate. Let's see the fourth postulate, which deals with composite system. So suppose we have, let's say, a container of gas, and then it contains, a few particles, or maybe you can think of like two striking billiard balls, and so on. So the joint state of the system is nothing but what can we easily infer from the individual states. For example, I can, if there is, particle m1, its evolution can be given by this equation, similarly for particle m2, and so on. And if we want to find out everything about the system, then all we have to know is the individual position of each particle. For example, if there are these two balls, so one is here and this one is here right now, so by knowing its position and its position, we can see what the total system is. And after they collide, and we can work out the change in momentum, and then again by knowing their individual positions and momentums, we know everything about the system. So a composite system in classical word is just sum of its parts. And once you know everything about the parts, there's nothing more to know about the system. You can say everything about the system that you want. For example, if I know the velocities of individual particles, I can compute what their temperature is. I can find out what their average kinetic energy is. I can work out the pressure, and so on. So everything about the total system can be known from after we know everything about the individual particles. So if we know everything about the parts, we know everything about the total system. So that is sort of the fourth postulate of quantum of the classical mechanics. And just as a side note, because this can help us when we are comparing quantum mechanics with the classical mechanics, is that We can, jointly stack individual particles in a total system, like this. For example, I can construct the position vector of all the particles by writing, let's say, the of particle 1's x, particle 1's y, particles 1 z. Similarly, particle 2's x position, particle 2's y position, particle 2's z position, and so on. So similarly, the momentum vector total can be written as by stacking the momentums of individual particles. And we can describe the whole physics of this system in terms of this big X and P vectors. Okay, so let's now go to the classical to the quantum mechanics and see what are the postulates that we can use to describe the classical the quantum world. So as I was saying earlier that when we discovered working with the microscopic world that it behaves differently from what our understanding was of the classical world based on our interactions with the macroscopic world, then slowly a new set of principles for our understanding of the universe was found, and I'm going to describe the basic set of principles or postulates that we now know that can help us explain everything in the world, all the way from the microscopic world to the macroscopic world. So right now I'm going to discuss only in simple terms, and then later on in the next couple of lectures we will build on it and make it more rigorous. So postulate number one is this, that the state of the quantum system is given by a state vector. Okay, and the state vector, let's say I call it psi, and we read it as psi ket. So this thing is, you can think of this as just a notation representing quantum state, and whenever we write this, we also have to remember that this means that it's a column vector. So we will represent the state as a column vector, and whenever this symbol is there, we will read it as ket, and this is the column vector. So the first postulate is that the state of all the uh, quantized systems can be represented by a state ket. And let's say the system is four level system, that there are only four possible eigenstates. I'll say more about eigenstates later on, but right now you can think of the eigenstates as the states that we can observe the system in. For example, if you think of the atom, so you can say that there are only four orbitals that are present in the atom that are allowed. So if there are only four allowable states, and let's say, let me call this as ground state, excited state 1, excited state 2, and excited state 3. So there are four states. So this means the state of the system can be written by this 4 by 1 column vector. And suppose I write it A, B, C, D, where these entries of this vector, they are now complex numbers, not real number, like classical mechanics. For example, this A can be 1 minus 3 iota, B can be under root 2 plus 0.7 iota, and so on. So these A, B, C, D are complex numbers, and the dimension of this state ket is equal to the number of total possible observable states of the system. So if it's a two-level system, it would only be a 2 by 1 column vector. If it is a 10-level system, there would be 10. And if there are infinite levels possible, for example, in an atom or in many other systems, there are infinitely discrete set of states that are possible. So in that case, this vector would be infinite. But in this course, we are only going to be dealing with finite systems. Okay, so another thing that is now different in quantum systems, other than that these entries can be complex, is this, that this vector always has to be normalized, and which means that a mod square plus b modulus square plus c modulus square plus d modulus square always has to be 1, where modulus is defined as modulus square is defined as a times a conjugate, and if a is 1 minus 3 iota, this means that 1 minus 3 iota, and conjugate simply means that you flip the sign of iota. So this number's conjugate becomes 1 plus 3 iota, and where, by the way, just to make sure that everyone is on the same page, iota is minus 1's square root. So this makes it 1 into 1, 1, minus 3 iota into minus 3 iota, 1 into plus 3 iota, and minus 3 iota into minus 3 iota becomes minus 9 iota square, and then this thing cancels out, and iota square is minus 1, so this becomes 1 plus 9 is equal to 10. So this a mod square is 10. So we have to make sure that whatever a, b, c, d are, their modulus square adds to 1. So that's the required property of this state vector is. And then this state vector has an additional property, and that is that, so I'm going to continue postulate 1, and additionally, if there is, let's say, this legitimate state, and then, and legitimate means that this is a normalized state, okay, and a, b, c, d, they are non-infinite complex numbers. They can be 0 but not infinite. And similarly, suppose if there is another state e, f, g, h, then we say that this is also a legitimate state of system. That if system can be in this state and the system can be in the same system can be in this state, then their linear superposition is also a legitimate state, where we have to make sure that alpha mod square plus beta mod square is 1, where alpha and beta are complex numbers. So let me just say what it means. So suppose I have a 4-level system, and one of the possible state is this. It has a little bit weights for each of the state, and then let's say there is another possible state psi 2. Then what we are saying is this, that a combination of these states psi given by this is also a possible state, provided that this alpha mod square plus beta mod square is 1. So this is called the superposition principle. Okay, so superposition also holds in classical world. There's nothing wrong about that. However, over there superposition works in a different way. So this also is perhaps a point to let me clarify it, that what these A, B, C, and D means. So the meaning of A, B, C, D is that if you have a four level system and then the state is given by suppose psi 1, then A mod square is the probability of measuring the system or state to be in ground state. So let's say this is the ground state, this is E1, E2, and E3. And similarly, B mod square is the probability that the system will be found in E1, and similarly, C mod square is that the system will be found in E2, and D mod square is that the system will be found in E3. So before we measure, the system is could be anywhere. It you know, perhaps anywhere is not a good word, but the system is in a superposition of these four states. But after we measure, the system can be found in one of these states with the probabilities that are given by the modulus square of these numbers. So let me state the second principle, and then I'll talk more about it. So second principle actually is second postulate of quantum mechanics, that measurements can, not always, but in general they can disturb the system. And this is unlike classical world. In classical physics, we assume that the measurements do nothing to the system, but in quantum mechanics, we know that it's the fundamental property of all systems in the world that the measurements can disturb the system. For example, if the system initially is in state psi, by the way, this I can also write like this: A G plus BE1 plus CE2 plus DE3, where again this is G and this is E3 and so on. So before measurement, the system can be anywhere, but after measurement, post measurement, the system is in only one of this state. For example, it might collapse to this one. We sometimes use the word collapse or projects. So the probability of finding the system in this after measurement is so A, B, C, D, so it's C mod square. And the state after measuring the system in E2 state is C E2 divided by C mod. So this is the state after the system has been measured, which I can write some. So let's just keep it like this for now. So the state after the measurement has changed. We say that the measurement process has projected the state of the system into one of the eigenstate of the system, or into one of the observable state of the system. And you see, we we are able to, and let's say if we measure the system many times, sometime the system will project it here, sometime it will project it here, sometime project it here, sometime here. And if I just count the number of uh, times that we have measured, and the number of times that the system has been found in one of these states, and plot this histogram, then these are my probabilities. So for example, we made 1000 measurements, and suppose like 200 times it projected to ground, and 300 times it projected to E1 state, and maybe like 100 time it projected to E2. And so this is 100, 200, 3 plus 3, 6. And suppose, so let me make this a little bit bigger. So 400 times it got projected to this. So like this is these are the probabilities. So after measurement, I can find the probabilities. Okay, this has probability of 0.1, this has probability of 0.3, this has probability of 0.4, this has probability of 0.2. But I don't have direct access to these numbers A, B, C, D. So this is like one difference from the classical mechanics. In classical mechanics, we represented the state of the system with a vector, position vector, momentum vector, but we could directly measure the component of position and momentum. But here we cannot measure A, B, C, D. We can only measure A mod square, B mod square, C mod square, and D mod square directly. And if we want to find out A, B, C, D, there is a very complicated process that we have to do, and it is sort of very difficult. So you can say that the universe prohibits us, or like tries to hide this state vector information from us, and we sort of directly have access to these mod square only. Anyway, so coming back to this postulate, so measurements can now disturb the system, unlike the classical mechanics where measurements couldn't disturb the system. So we will, have much more to say about measurements later on. But let me move on to the second postulate, the third postulate. So the third postulate is evolution of state. So how do the state change? Evolution of state. Since the state is a column vector, and then after evolution, the state will still be a column vector of same size, because if it is a four level system and we do something to it, and it goes to another state, so that is still a four level system. So in general, we can think of uh, the state transformation as the matrix, that a matrix sort of mediates this state transformation. Let's call this matrix U, and this has to be a 4 by 4 matrix in general. But this matrix cannot be just any matrix, because we have to make sure that the normalized state is transformed to the normalized state. Because if this is a legitimate state, we already know that A mod square plus B mod square plus C mod square plus D mod square has to be 1. So this has to be a matrix that that transforms this normalized state to a normalized state. So to make sure that this is a normalized state as well, this matrix has a restriction on it, and we will work out in detail later on. But this matrix is called a unitary matrix if it preserves the normalization of the state. And this has this special property that the its inverse is simply equal to its transpose and then its conjugate. So as an example, if let's say I'm talking about a two level system, and then let's say I have a U11, U12, U21, U22, then U transpose and conjugate would mean that U11 conjugate, U21 conjugate, U12 conjugate, U22 conjugate. So we took the transpose and we took the conjugate of each elements. And conjugate again means that we have to flip the sign of iota. By the way, this writing of T and conjugate again and again. So since we encountered these unitary matrices a lot, uh, we simply represent it with this symbol dagger. So this dagger essentially means that there is a transpose and there is a conjugate. So a unitary matrix has this property that its inverse is equal to its transpose and conjugate, which we will represent as U dagger, which means that if I take the dagger of U and multiply it with U, we will get identity because this U dagger is the inverse. So it means that the evolution of state is given by it's the product of the state with the unitary matrix. So in place of the evolution of state in classical physics using Newton's laws, we have the evolution of state through the unitary matrices so that the normalization of the state is preserved. Let's go to the final postulate, which deals with composite system, that how do we treat composite quantum system. So this is our postulate number 4. Suppose we have a 2-level system and a 3-level system. So suppose I have a state 1 for this system and state 2 for the other system. So suppose this is AB and then A, let me not use ABC, let's use different symbols. So C, D, F. Okay, so the fourth postulate is that we combine the system using tensor product. So psi1 tensor, so this is read as tensor and we call this tensor product. So let me just explain what this tensor product is. It's actually very simple, even though a little bit counterintuitive. So what we do, we take the first element of this matrix and multiply it with each of the element of the second matrix, and then we take the second and we multiply it with each of the element of the next matrix. All right. So this is the joint state description of these two systems. So let's say, so we can put a tensor here. By the way, sometime people would just write it as psi1, psi2 and be lazy and not put this tensor. And we will also be doing it, many times that we might be omitting this tensor symbol just for the sake of, shorthand notation. So when you see this state written like this, it actually means this, that there is a tensor product between the states. So similarly, if the main thing is this, that how do the properties or postulates of individual systems they play out for the composite system. So let's see that. So continuing the composite system. So the principle of superposition applies to composite system as well. Superposition principle applies to composite system. For example, if there are two systems and then there is some, joint state of these two systems, let me call it some psi 1 in terms of this system. So let's say this system has A1 and this system has B1 state. So this is one joint state, and let's say the individual systems also has some individual states A2, B2. So there is this joint state as well, and there's this joint state as well. So the principles, the superposition principle also applies to this joint state, that provided that alpha mod square plus beta mod square is 1, which means that we can write it like this: A1 B1 beta A2 B2. And you see I omitted the tensor symbol because I don't want to write it again and again. All right, so this joint state is now sort of is intriguing, because when I measure the joint system, the total system will either collapse to this state A1 B1, or it will collapse to this state A2 B2. So first of all, so this is something that when we measure a state of the system which is a joint state of the system, then it will project to either this or this. On the other hand, if I measure only part of this whole system, for example, you only measure this system and you don't do anything to this. So when you measure this system, you will either measure this one. After measurement, you will either get A1 or you will get A2, right? And if you get A1, the other system will automatically collapse to B1, because the joint state has to collapse to one of these parts. And if you measure this system, this part in A2, then the other system will automatically collapse to this state B2. So this phenomena of measuring part of the system and disturbing the state of the whole system has a lot of applications, and we will talk much more about it. This is called this is a special state. It's called the entangled state of these two subsystems, and we will be talking much more about the entanglement of systems, because there are special states of joint systems that we call entangled states, and they give rise to many intriguing properties of quantum systems. And this is also sort of a combined state, which is sort of which has more information in a way than the individual system states, because one of the measurement of one system disturbs the other system, and we will be talking much more about it later on. So let's conclude this lecture, and let me just summarize the what we did today. We started by discussing the classical and quantum system. So in a nutshell, the classical world is the macroscopic world that we see around us, and the quantum world is usually the microscopic world. But sometimes there are many macroscopic objects like stars and even superconductors, and there are some other systems where we can directly see the impact of the quantum states. And what we realize that the laws of classical physics are more precisely the laws of physics that we discovered by observing the classical world. They don't really apply when we go to the microscopic world. And in the last 120, 30 years, we have come up with a new or modern understanding of the world around us, which is described by the laws of quantum mechanics or quantum physics. And just to emphasize at the end again that never think that we have sort of a dichotomy, that okay, there's big world where classical physics applies and there's a small world or microscopic world where quantum physics applies. That's not the case. You can explain the whole universe from the microscopic scale to the macroscopic scale using quantum physics, but the classical physics laws are mostly only applicable when we are dealing with the macroscopic scale. So we can think of classical physics as sort of approximation of quantum physics when we are dealing with the macroscopic objects. And the major difference between classical and quantum physics is that in the classical physics, our objects live in phase spaces, which are composed of position and momentum coordinates of the particles. And we can describe a composite classical system as just the sum of individual classical particles. And once we know everything about the individual classical particles, we can describe the all the properties of the composite system. On the other hand, the quantum systems, they are governed by state vectors, which are normalized state vectors, and such that their individual components give us probabilities of measuring those one of the eigenstates by taking their modulus square. And since those they we call the set of all possible states of a system a Hilbert space. I'll have much more to say about Hilbert space, because this is a vector space that has like a way of measuring the length of the vector. We call it inner products. We will say much more about it. So the quantum system are sort of system that lives in a Hilbert space. That is, that their state is given by normalized vectors. And then just the last few words, that the state of quantum systems, its evolution is given by the unitary matrices or unitary operators, and that's what we will talk in the next lecture. So, with this, this lecture comes to its conclusion, where we talked about the classical and quantum physics. In the next lecture, I'll go much deeper into linear algebra that is required for quantum systems, and we will the build on the mathematics that is required for quantum mechanics, and then we will introduce what are quantum computers, and how to understand the workings of quantum computer, and how to use them to solve real problems, and how to implement programs on quantum computers. Thank you very much for watching this lecture, and I look forward to talking to you next time.